Technical difficulties with the projector connection system. It refuses to cooperate with my computer, which means I have no visual for the room, and more importantly, no audio. I cannot hear a word anyone says. So if you have questions or comments during class, you need to type them into the chat. Well, except you can obviously speak out loud. That still works. But if you would like a visual aid, you will need to join the Zoom. All right. I think that about covers it. Let me pin the video link to the classroom here. And then we will get started. So the first thing we are going to do is go over answers from last Thursday's work. So let me pull that up on screen, and I'll give you a couple moments to look at it, and I'll talk more as we go. Maybe we'll start at the top. There we go. Questions on the first page of answers here? Fairly straightforward with the names. Number 8, there are some options here. Of course, you do not need to put this one before that one. You can switch those places. And since these are just segments and not rays, the order of the letter doesn't matter. I can call this segment NK instead of KN, just like they point out here in number 3. So that will work there. Number 9 has you calculating the midpoint. This is a favorite question on the SAT. They love having that somewhere. You need to know the midpoint formula. It's just average. It's literally the average of the x's and the average of the y's. And I'm going to try to get this working as we speak here. Get that in there, get this plugged in here. Hey, stop that. Hey, excellent, thank you. Why does it say no signal? All right, but yeah, so that's all midpoint is, right? It is the average of the two there. So in this question, they actually give us the coordinates for the midpoint. So we're going to work backwards here. -4 is equal to 6 plus x over 2. Solve for the new x and y, or maybe the old x and y, depending on how you think of it, to find your coordinates for E there. Okay, I finally got my second screen up, and the first screen goes blank. What's happening now? Now I can't see what I'm doing here. Oh, there's everything. All right, well, at least now you can see in person. All right, I'm going to keep going. Things are going to get a little weird here. So, number 12, it only asked you to sketch the 6 points. You did not have to draw in all of those lines, but I did, and I color-coded them to hopefully make things a little easier. And the names there are listed. I use red around the outside. That's just connecting them each in alphabetical order, and then you start getting all the extra crisscrossy bits for a total of 15 lines. And then 13 here with the cube. This is requiring you to think a little bit in 3 dimensions here. We're really going to stretch that visual spatial manipulation. Okay? This is a 2-dimensional picture of a 3-dimensional cubic object. The points they give B, C, H, and E I have out connected here in red, so that is a diagonal slicing of the cube. They result in those 4 being then on the same new face. If we were to cut it in half and open it up, you can see they're all on that flat surface created by the slice there. You could slice that diagonally any number of ways. So here's another option in green, B, D, F, H, all cut there. Hey, if I just give it enough time, figure things out. Here we go. Back to 2 monitors. Awesome. And then the easy ones, of course, is to just go with one of the faces, all 4 right there. Altogether, you could do any of the 6 sides. There are 6 diagonal slices, so a total of 12 sets. Okay, questions on that page? No? All right, lost some time for technical difficulties. I'm going to have to move fast here. So, stop me at any point. On to the next page, matching the terms with the pictures. There they are. D, E, F, H, G, C, I, B, A. Fairly straightforward. Again, being able to recognize them visually as well as interpret their meaning is more important for me than written definitions. Speaking of interpreting meaning, understanding what complementary means here is critical. If they're complementary, that means their measures are going to add up to 90 degrees. That's what this means. The measure of angle Q plus the measure of angle R is going to be equal to 90. And then it's just a substitution. They give us this number. Substitute that in. Solve for the measure of angle R. Subtract 77 from both sides. Simple algebra. You're going to get 13 degrees. And then when they say, what can you conclude about angle P and angle R? Well, they're both equal to 13 degrees, right? So you can state that. You can write that out in words. You can write they're equal to each other. They are congruent to each other. I wrote it as a mathematical equation here. The measures are this equals that equals 13. Okay? It's all right there. That's the condensed mathematician format. However you wrote that is fine. And then finally, we have some pictures. 2 parallel lines, one of them marked as perpendicular. Make sure these are marked as parallel. Add matching sets of arrows in the middle of the lines. They can be oriented any way you like. If they're turned around this way, upside down, that doesn't make a difference. So there's lots of ways your picture could look specifically. Same with this guy here. You need this ray, P to R, and PQ needs to be perpendicular to that and marked as such, but it could go up here. The whole thing could be turned, rotated, flipped backwards. That's fine. And 13 is the most complicated. 13 asks you for 2 angles that are congruent to each other. You could have drawn these almost as vertical angles. There's one. There's the other. So long as the angles match, that's fine. Or you could have the second one, over here somewhere, right? That could be fine. These could almost look like intersecting lines. Exactly how they are oriented is fine, so long as they meet at that point. And then you need to set the distances or set your labeling such that B to C is equal to C to X. So you're probably going to need C to be between those two equally. You could even go on the far extreme would be two perpendicular lines, as long as if that's C, you've got B on one side and X on the other. Of course, A would be in the middle and Y would be down here. That way you can have a nice equal-sided isosceles triangle there. And that could work. All right, questions on that page? No? All right, then onward to the new stuff of the day. Sections 1.4 and 1.5, polygons, and specifically triangles. So a lot of this should be review. Again, heavy emphasis on the vocabulary. It's going to feel rushed this week. I totally understand that. We're just laying down the groundwork. The important thing this week is the vocabulary. Make sure you know what each term means and it brings to mind the same picture in your head. Later, for the rest of the quarter, we will actually be doing more manipulations with this. All right. I think everybody can fill out half of this table as we go. But join me. Let's get some answers in chat here real quick. Starting at the top, a polygon has how many sides for the triangle? That means how many sides for the triangle? Type it in chat. I've got one, I've got two. That's number of answers. I've got one answer, I've got two answers. They both agree so far. Can I get another vote? What do we think? There it is. Yeah, 3 sides to a triangle. Oh, that's easy mode. All right. Let's see. This goes 3. We skip 1, go to 5. So inductive reasoning would tell me a 4 should go here. Agreed? All right. What do you call a 4-sided polygon? He says square. He's technically not wrong. A square is a 4-sided polygon, but is every 4-sided polygon a square? No. No. What's the general term? Chat's got you covered. Quadrilateral. Very good. Carlos and Ariel on the ball here. Quadrilateral. Literally 4 lines. That's what that means. Okay, and I think these first 2 columns, we can go down pretty easy. Name for a 5-sided figure? Type it in the chat. Let's see, Carlos is on top of things. Pentagon, thank you, Carlos. All right. And I'm pretty sure we know hexagon is six. Heptagon is 7. He's got it. Good. 8-sided figure. If you're learning to drive, you're going to be seeing a lot of these. Octagons, very good. All right, oh wait, we got double blanks here. Shoot. I don't know that this is automatically 9. That would be the next one, right? Counting up, it would be 9, but then they go straight to 12. So I cannot be certain that it goes 9, then 12. I don't know that they, so let's fill in 12. Does anybody know the name for a 12-sided polygon? And then we'll go back and try to determine which one should go here. 12 sides really test your Greek here. That's where all of these names come from. These are all from the Greek. Penta is their word for 5 gon meaning shape, I guess. Carlos says decagon or dodecagon? And Ariel comes in with another vote for dodecagon. Very good. Do for 2, deca for 10, like a decade is 10 years. So 2 plus 10 makes 12. Dodecagon. All right, so there's the names. What do we think goes in here? Well, in order to determine that, the only thing they give us is the number of diagonals. So if we can determine which one has 35 diagonals, we'll know for certain which one should go there. It's probably between 8 and 12, right? So it could be 9, 10, or 11. You can at least narrow it down there. Which one is it going to be? Let's see if we can find a pattern for number of diagonals and fill it in. Ariel's already got a guess here. That's a good instinct here. Let's see if we can be certain. All right. Number of diagonals you can draw in a triangle. A diagonal connects 2 vertices, 2 of the corners, but that's not already a side. So 2 non-adjacent, right? You got to like be able to skip one and go to a next one. A triangle doesn't have that. I have no diagonals there. Good old quadrilateral, of course. We can go, oops, it's not giving me the line tool, right? We can't go straight to there, that's already a side, so we can skip to there. We can skip to there, that's 2. How about pentagon? Make a quick sketch. 1, 2, 3, 4, 5 sides. And this guy goes to there, there, here. Nope, that's already a side. There, there, there. Looks like 5. All right, how about 6? I'm going to save myself some time. I already drew 6. Back here, I drew 6 points. I connected them all. The red lines make 1, 2, 3, 4, 5, a 6-sided figure. How many diagonals are there now? How many lines were there total? And 6 of them are sides, right? So we can subtract off those 6 for a number of diagonals. Should be 9, right? Okay, so 9 goes here. We don't have to draw that all over again. That's going to get tedious. Let's see if we can find a pattern here. Maybe we can inductive reasoning our way through this instead of having to draw out each one and count by hand. From 0 to 2, we added 2. From 2 to 5, we added 3. Ah, crap. It's not consistent. They didn't go up by the same amount each time. Dang it. Well, let's keep going. Maybe there's a different pattern. From 5 to 9, we added 4. Anybody spot a pattern now? These weren't the same differences, but the differences between the differences is +1, right? That part is just counting, so I can easily determine this should go up by 5, right? And 9 plus 5 is what? 14. Right? All right. Carlos is doing awesome in the chat. Thank you, Carlos, so much. I need more people throwing some answers in the chat. I know you got to switch back and forth to your page. You're filling it in, and switching to Zoom. It takes a little time. Work that Alt-Tab. Okay? All right. Then this one goes up by 6, and so next we should have chat, please. Got 2 answers? What was the question? What number goes here? How many diagonals for a octagon based on the pattern we've seen so far? I'm seeing some good answers. I want to see if Ariel will get it now. Yes? Sure. Ariel, do you have an answer? Number of diagonals for the octagon? You don't know? Follow the pattern. We've just been adding up these numbers. 14 plus 6 is how many, Ariel? You can do that. 20. See, there you go. I knew you had it. Right? This is the power of pattern finding, folks. You don't need to know necessarily, like, have memorized, oh, octagons, those have 20 diagonals. Follow the pattern. In fact, if we continue to follow this, I'm going to switch to a different color here just in case. We would expect to add 7, right? 20 plus 7 is 27? That's not 35. These go up by 1 each time. So if I increase the number of sides by 1, that's following one step in the pattern. I didn't follow just one step here. So this cannot be 9. Let's check. If I go up 1 more, 27 plus 8, that is 35. So this is not 1 higher than this. This is now 2 extra sides here. So that means this guy is a 10-sided figure called the decagon. Right? Dodecagon was 12. Decagon is 10, just the decade part. And now my displays are really fritzing. I got this part to cooperate. Now the computer is throwing fits. All right, but it seems to still be broadcasting, so we're going to keep going. I'm going to erase this pink stuff here. That was just the possibilities. Blue is the correct answer. I'm going to leave this one open for you. You can either continue to follow that pattern, or if you really want to challenge yourself, find a formula that takes us directly from number of sides to number of diagonals. What function could I use that'll input a 6 and give me out a 9, input a 7 and give me out a 14, input an 8 and give me out a 20? That's kind of an interesting one there, isn't it? Because at this point, we go from less than double to more than double, and so that's really going to take some thinking there. So I encourage you to give that a try. Now, the rest of this section, pretty straightforward, so long as you understand these vocabulary terms. Drawing a pentagon is easy. Label the points, this, and this, fine. Okay, but the new term here is a concave pentagon. Maybe you haven't seen that. Most pentagons, you're going to draw something like that. 1, 2, 3, 4, 5 sides. A concave pentagon has collapsed. Okay? Somebody has pushed way too hard on one of the corners and caused it to buckle inwards like that. And so now instead of that guy, we've now got this. The test for whether or not a polygon is concave is whether or not one of the diagonals lies outside of the polygon. So remember I said a diagonal connects 2 vertices, but it's not already one of the sides. Right? If you're just drawing over the side, that's not a diagonal. This connects two vertices. I didn't draw over the side, but I did end up entirely outside the figure. So if any of it goes outside, it's a concave figure. Okay, so there's your concave pentagon. Go ahead and label that with the features there. Bless you. Equilateral. Equilateral here being equal, lateral being sides. So we have to make sure all of our sides are marked equilateral. It's a quadrilateral. You can draw it however you want for your four sides to be. Right? Just make sure you mark things congruent that are supposed to be congruent. They don't really have to look the same. Okay, you can draw a nice like long skinny thing if you want to and say near, those are supposed to be the same. I will believe you, but please don't make it any harder than necessary. Try to at least make it look reasonable, okay? But that could be valid right there. This could be your start. That is allowed. The marks override whatever it looks like. Okay. All right, 15 through 18. Use the figures at the right. They tell us MNOPQ is congruent to RSTUV. These two shapes are the same size, same shape. In fact, if, let me trace over this one so I can pick it up and move it around. I could take this shape, move it over on top of this one, and just from rotating it around, like matching puzzle pieces, it could fit, at least it should fit, right on top of the other one. And everything will correspond as such, okay? So you need to look and see which angle corresponds with which angle, which side corresponds with which side. And all of these measurements are given, if not in one shape, then they are available in the other. There shouldn't actually be any calculations required here. All right? This will be matching the correspondence from congruent polygons. You'll be seeing that a lot. SAT loves to try to trick you with this thing. They actually just give you the information, but they make it really harder to read. Okay? And then I hope you all remember perimeter, add up all of the sides, okay? And then what regular is going to mean about the relationship of each of those sides, so you can determine them just from the one perimeter length. I'll let you think on that. Any questions on this page then? No? All right, then real quick, let's go on to the next one. Here we start with naming things from the figure. So parallel lines are a big deal on the SAT. We're going to spend a couple days on that all by itself. So spotting these elements, and you're finding the parallel, the perpendicular, right? Naming and identifying each one from there. Very important skill to have. So be able to identify all of those. That's all you got to do is write out the names of them. Where are the parallel segments? Well, you look for the little marks. That's this line here. That's another one there. That's this line. Okay, how can we name those two lines? There's multiple answers for each of these because there's multiple ways to name them, and some elements are there in multiple ways, okay? Next up, the specific triangle types. I hope you remember these from way back when. They're going to ask you about isosceles, obtuse triangle. Isosceles. Oh, that's one of those triangle classifications. We've got isosceles. We've got scalene. Or it could be equilateral. Right? All of these have to do with the number of matching sides. Right? How many sides are congruent in an isosceles triangle? Type it in the chat. How many sides are congruent in an isosceles triangle? I've got one answer. This is what I mean by you've got to get familiar with these terms. This should come automatically. I'll give you a hint here. Scalene has no congruent sides. None of the sides match. Equilateral means all of the sides match. You've got 3 matching sides. Not a whole lot of options left. Isosceles has how many? Got two answers now? Giselle's unsure. She says 2 question mark? Yes, it is 2. Good. We're running out of numbers. You can't have one matching side. What would it be matched to, right? That just wouldn't make sense. Although you can make a statement about something being congruent to itself. That is allowed. And we might find that such a thing useful in the future. But anyways, isosceles has 2 matching sides. That means when you draw your triangle, 2 of these better be indicated as the same length as each other. All right, next up, not just any isosceles triangle, but an obtuse triangle. What do you know about obtuse triangles as opposed to acute and right? They all have something to do with the angles. Type it in the chat. What makes a triangle obtuse? I've got one answer. Very good, Ariel. Yes, that is correct. Anyone else? And don't leave Ariel to do all the work here. Ooh, my package was delivered. Excellent. I got a new shirt. Greater than 90, Carlos says. Yes, greater than 90 degrees. That is to say, one of the angles is greater than 90. This, of course, applies to one angle. Acute means less than 90. Actually, let me put that number over here, because only one of them can be more than 90. Otherwise, you don't end up with a triangle. In an acute, all 3 of them will be less than triangle. And in a right, you have one of them is exactly 90 degrees. So we want an isosceles obtuse triangle with the vertex angle T. Vertex angle is the special angle. So when you draw an isosceles triangle, you say this side is the same as that side. One of these angles is different than the others. One of them stands out as unique, right? These guys down here will match because these 2 sides are matching. This guy stuck in between them is unique and stands out, and that is the vertex angle right there. I, of course, did not draw my triangle obtuse here. So please rectify that on your own drawing, but this would be your vertex angle, and that should end up T. You can put the rest of the letters where you like. Spread this thing out a little wider, right? Make that obtuse, and you'll be good to go. Then similarly, we got scalene, right triangle. Okay, we talked about those terms. Add some midpoints to it. That's just piling more things on top of the drawing. That doesn't change the triangle at all. All right, and then the last section, using the graph at the right. The SAT loves to make things more complicated. It likes to take the algebra and the geometry and merge the two together, saying, hey, you know how we can make geometry harder? We're going to put it on top of our Cartesian plane. And instead of just dealing with the ideal world of shapes and concepts related thereof, you have the specific coordinates of everything to keep track of. It's a lot more numbers thrown at you. But the ideas are all still there. So if you look at this coordinate plane, as already drawn, I have points A, B, and C here. I can connect the dots. I can make a triangle. Notice this is going to be a right triangle. Anytime I have two of the sides right on top of the graph lines, it's automatically a 90-degree angle, automatically a right triangle. So really, the Cartesian plane can make some things actually easier for you. But the questions here are not asking about the existing triangle. They say locate F so that triangle ABF is a right triangle. Oh, I drew triangle ABC. So what we want to do is we want to make a new point. I'm going to erase these sides for now. We're going to make a new point called F. Don't draw that yet because I'm going to move that around. Where on this can I put F such that A to B to F? So I definitely need line AB. I can at least keep that one. And then we got to connect them to F. Where is that going to be a right triangle? Now the cop-out answer is to put it right on top of C. Don't do that. All right? You can't have 2 points occupying the same place. That's cheating. Okay? Only 1 point per intersection. All right? So pick a different intersection. If I put it here, be a right triangle. There's a right triangle. Right above C, right below C, on the other side by A, right? You have to determine something like that. There's a lot of answers here. You can put it anywhere you like. I'm gonna pull an easy one. 1, 2, 3. So I'm gonna go opposite. 1, 2, 3. I'm gonna flip my triangle upside down. We'll just go down here. So there's one option. Right? This is a 90-degree angle. Pretty much anywhere along this line. If you put F anywhere up here, it'll make a right angle with AB right there. So that's a freebie one for you. But that's not all they wanted. They said, what's the location? So I got to count off. This is 8, comma, 1, 2, 3, -3. So my answer to this question would be the location of F, the coordinates, 8, comma, -3. Okay, be sure to do that part. Rewrite your answer over there. That's what they're asking for. And then similarly with 11, 12, put D and G to make these other kinds of triangles. All right? Questions on that page? Okay. We've got 5 minutes left. Go ahead and answer what you can. You can maybe get 3 or 4 more questions in before the end, and then finish off the page by tonight, and you're good to go.